Today we talk about classification of singular points. So before we enter into the topic, I want to discuss some basic definitions involved in this topic. The very first one is analytic function. A complex function f of z is said to be analytic at a point z is equal to a if it is differentiable at every point of some neighborhood of a, that is modulus of z minus a less than r. In other words, derivative exists not only at that point but also some neighborhood of that point. So here the function is analytic at a point z is equal to a. That means we can construct a small circle around the point a. So each and every one of this neighborhood contains a point. As in that point also the function is analytic, not only at this point but also some neighborhood of that point. That means each and every point of this neighborhood containing the point is also analytic. Then the point we can call it as analytic of a complex function. Point we can call it as analytic. The function we can call it as analytic function. So whenever you come across modulus of z minus a less than r, so here a is any complex number. A is any complex number. For example, if it is given like this, z minus 1 equal to 2. So, it represents a circle with a center at 1, 0 and radius is 2. Suppose if it is given like this, because already I told you a is any complex number. Complex number means it can be expressed in the form of x plus iy. Suppose if it is given 1 plus I equal to 2. So it is a circle, it represents a circle with the center at 1, 1 and radius is equal to 2. Like this we can define a circle. Okay. So whenever you come across this, you can represent it as a circle with the center at, depending upon the value of a, you can write center as well as radius. For example, f of z is equal to z squared. So first you can manipulate derivative. So 2z. For all the values of z, what is your z? Z is a complex number. For all the values of z, derivative exists. Therefore, we can conclude that the given function f of z is analytic. So what is the definition? Not only at that point but also some neighborhood of that point. If I construct a small circle around the point, each and every point in that neighborhood is also analytic. Derivative exists. That is a definition for analytic function. Next we talk about, this is the diagrammatic representation of analytic. So here the point derivative exists not only at that point but also some neighborhood. Neighborhood in the sense, if we construct a small circle around the point, each and every point in that neighborhood, the function is analytic. F of z is analytic at every point inside the neighborhood. So next we talk about singular point of a complex function. A point z is equal to a is called singular point of a function f of z or singularity of the function f of z if f of z is not analytic at the point z is equal to a, but it's analytic at every point in some deleted neighborhood of a. So f of z is not analytic at the point z is equal to a particular point, the function is not analytic, but if I construct a small circle around the point, the function is analytic. That is a meaning. Deleted neighborhood of a, that means the point a is not analytic, not included in the neighborhood, deleted. That is a meaning. Okay, how we are going to represent deleted neighborhood? 0 less than modulus of z minus a less than r. That means this point a is not in the neighborhood, does not contains a point. For example, f of z is equal to 1 by z minus 2. So how do you analyze the singular points of the function? 1 by z minus 2. For what value of z the function is not defined, put z is equal to 2. 2 minus 2, 0. 1 by 0, infinity. The function does not exist at the point z is equal to 2. Therefore, z is equal to 2 is a singular point. If I construct a small circle around the point, each and every point in the neighborhood, the function is analytic. So, if I construct a small circle around z is equal to 2 means, so for example, if I consider a real line, okay, this is 0, this is 2. If I construct a small circle around 2 means, so apart from 2, so what about right side of neighborhood, the point 2, so 2.1, 2.2. If I put z is equal to 2.1, 2.2, similarly in the left side also 1.9, 1.2, the function exists. Am I correct or not? So what is the definition for singular point? Function is not analytic at the point, but it is analytic every point in some neighborhood of that point. So okay, can you able to understand the concept? The function is not analytic at a particular point, but it is analytic in the neighborhood of that point. Okay, so like this we can define the singular point of the function. So this is the diagrammatic representation of a singular point. So the function is not analytic. F of z is not analytic at the point, but it is analytic every point in the neighborhood of that point. So f of z is analytic everywhere in the neighborhood, everywhere in the neighborhood. Okay, so deleted neighborhood means this point is not included in the neighborhood. That is, we can conclude that deleted. The function is analytic every point inside the circle except at the center point A. That we can conclude that deleted neighborhood. We can represent it in this manner. The representation of the deleted neighborhood is 0 less than modulus of z minus a less than r. This simply, if I write like this is a neighborhood. Okay, 0 less than means deleted. That means the point A is not included in the neighborhood. So this is the easiest way you can compare the analytic and singular points. You can easily observe the concept. Analytic at a point, analytic in a full neighborhood. Not only at that point, but also in some neighborhood of that point also the function is analytic. Singular at A, not analytic at A. The particular point is not analytic, but analytic in a deleted neighborhood. It is analytic everywhere in the neighborhood of A except A. Okay, center point is included. Here center point is excluded because that particular point only the function is not analytic. Okay, for example, f of z is z squared. For example, f of z 1 divided by z minus 2 as a singular point at z is equal to 2. This is analytic everywhere. So you can easily remember the concept. Next we talk about types of singular point. So before we talk about types of singular point, I am going to discuss isolated singularity and non-isolated. We have two different types of singular points, isolated and non-isolated. So what do you mean by isolated? A singular point z is equal to a is called an isolated singularity of the function f of z if there exists a neighborhood of a in which there is no other singularity of f of z. If there exists a neighborhood of A, already I told you neighborhood of A means we can construct a small circle around A in which there is no other singularity other than A. The neighborhood should not contain any other singular point other than A. Okay, then we can conclude that the point A is isolated singularity. For example, f of z is equal to 1 divided by z minus 2. The function is not analytic for all except z is equal to 2. Therefore, there exists a deleted neighborhood. Deleted means the particular point is not included, in which z is equal to 2 is a only singular point. Therefore, z is equal to 2 is an isolated singular point. That means the neighborhood of the point z is equal to 2 does not contain any other singular points other than 2. Then we can conclude that isolated singular point. This is the representation, graphical representation of isolated singular point. So this particular point, the function is not analytic. Apart from this, the neighborhood should not contain any other singular points. So it is a isolated singular point. So next we talk about non-isolated singular point. So non-isolated means a singular point which is not isolated is called non-isolated singularity. That is, every neighborhood of the singular point contains at least one other singular point of the function. Isolated means the neighborhood of the singular point does not contains any other singular point other than that point, a singular. Okay. Non-isolated means the neighborhood of the singular point contains at least one other singular point other than that particular point. It contains other singular point of the function. For example, f of z is equal to cot 1 by z. Okay, so how do you express cot 1 by z? Cos by sine. How do you manipulate singular point of the function? Already I told you denominator term will be equal to 0, will gives singular points. So sine of 1 by z is equal to 0. For what value of sine sine theta equal to 0? For what value of theta? Sine 0, 0. So theta can takes a value n pi. Suppose I can assume that this 1 by z is w. So how do you express sine w equal to 0? So w is equal to n pi for all the values of n. If I put n is equal to 0, 0, sine 0, 0. If I put n is equal to 1, 180, 0. Minus 180 also 0. 2 pi 0. Minus 2 pi is also 0 for all the values of n. Replace w by 1 by z. 1 by z is equal to n pi na. What about your z? Z is equal to 1 by n pi. So n can takes a value plus or minus 1, plus or minus 2 and so on. Since 1 by n pi tends to 0 as n tends to infinity. Am I correct or not? If I put n is equal to infinity, 1 by infinity is 0. So every neighborhood of z is equal to 0 contains infinitely many singularities. Therefore, z is equal to 0 is a non-isolated singularity. Am I correct or not? Listen, I will explain with the graphical representation, diagrammatic representation of this. So what is given? Z is equal to 0 is a non-isolated singularity. Z is equal to 0. If I construct a small circle around Z is equal to 0. If I construct a small circle around Z is equal to 0. See, these are all singular points. 1 divided by n pi. If I put n is equal to 1, n is equal to 2, n is equal to 3. 1 means 1 pi. N is equal to 2 means 2 pi. N is equal to 3 means 3 pi and so on. As n tends to infinity, n can take a larger value. So what happened? This z tends to 0. Am I correct or not? N can take a larger value in the sense 4, 5, 6 up to 1000. 1 by 1000 pi, 2000 pi. It can take some finite value, infinite value, larger value. The z value tends to 0. Z value tends to 0 means what? If I construct a small circle around z is equal to 0, what happened? So it contains at least some singular point other than 0. Am I correct or not? 1 by pi, 1. You can plot the point on the real line, then you can easily understand the concept. It contains, the neighborhood contains other than singular point, z is equal to 0. Therefore, z is equal to 0, we can call it as non-isolated singular point. Can you able to understand the concept? Yes, okay. Like this we can define. So next we talk about types of isolated singular points. An isolated singular point z is equal to a of a function f of z may be classified into the following three types. Number 1, removable singularity. Number 2, pole. Number 3, essential singularity. So we can define the removable singularity, pole, essential singularity based on the expansion of Lorentz series. So here, this is the expansion of Lorentz series. Already you know that Lorentz series expansion contains both the positive as well as negative powers of z minus a. Z minus a. Am I correct? So here the positive power of z minus a we can call it as analytic part. Negative powers of Lorentz series expansion we can call it as principal part. Your f of, this is the Lorentz series expansion. The positive powers of z minus a in the Lorentz series expansion we can call it as analytic part. Negative powers of z minus a in the Lorentz series expansion we can call it as principal part. So depending upon the principal part only we can define whether the singular point is removable, pole, essential. So no negative powers in the expansion we can call it as removable singularity. Finite negative powers in the expansion, if the expansion contains finite number of negative powers, then we can call it as pole. Infinite number of negative powers, now we can call it as essential singularity. Okay. So I want to explain the types of isolated singularities one by one. The very first one is removable singular point. A singular point z is equal to a of a function f of z is called a removable singularity if the principal part of the Lorentz series means negative powers of z minus a about z is equal to a is identically zero. Identically zero means no negative powers. So the expansion contains only positive powers of z minus a. In this case, f of z can be redefined at z is equal to a so that it becomes analytic at a. For example, f of z is equal to sin z by z. At z is equal to 0. So already we know that how do you manipulate singular points? The denominator term will be equal to 0. So z is equal to 0. So we can expand the expansion sin z. You know the expansion of sin z, x minus x cube by 3. So okay, sin z by z means you can take one z term as a common factor. So 1 minus z squared by 3 factorial. So in this expansion, it does not contains any negative powers of z. Since there are no negative powers of z, the principal part is 0. Therefore, z is equal to 0 is a removable singularity. In the expansion, Lorentz series expansion does not contains any negative powers of z minus a. Then the expansion, then the singular point, we can call it as removable singular point. So we can define removable singular point in another manner also by using the limit. An isolated singular point z is equal to a of f of z is called removable singularity if limit z tends to a f of z exists and is finite. You can easily remember this concept. The same example I can explain sin z by z. Limit z tends to 0 because the singular point is z is equal to 0. Sin z by z. If I apply z tends to 0, what happens? Sin 0 by 0. So sin 0 means 0 by 0 form. This is an indeterminate form. So what we are going to do? We are going to apply L'Hospital rule. Differentiate numerator and denominator separately. Differential of sin z is cos z and differential of z is 1. Now you can apply the limit as z tends to 0. What is cos 0? Cos 0 value is 1. So limit exists and it's finite. Therefore, z is equal to 0 is a removable singularity. So we can find a removable singularity in two different manner. One, if it is possible to expand the given expansion f of z as a Lorentz series expansion, then the Lorentz series expansion should not contain any other negative powers. Then I can easily conclude that the given singular point is removable singularity. In other words, we can use this formula, limit z tends to a f of z exists and it is finite. Then I can easily conclude that removable singularity. Okay. So next we talk about pole. A singular point z is equal to a of a function f of z is called pole of order m if the principal part of the Lorentz series about z is equal to a contains finite number of terms. That means the Lorentz series expansion contains finite number of negative powers of z minus a. Then I can conclude that it is a pole of order m. See, this is the expansion of Lorentz series. In this expansion, it contains negative powers, finite number of how many negative powers of z minus a? 1, 2, how many number of terms? Finite number of terms, m terms will be there in the Lorentz series expansion. Then I can conclude that it is a pole of z is equal to a is a pole of order m. For example, f of z is equal to 1 divided by z minus 2 the whole cube. So first you can manipulate singular points. Singular points means denominator term will be equal to 0. So z minus 2 the whole cube is equal to 0. That is z minus 2 equal to 0. That is z is equal to 2. So here z is equal to 2 is a singular point of the function. So after that only we can identify whether it is a removable singularity, pole or essential singularity. Okay, so f of z is equal to 1 divided by z minus 2 the whole cube. So here it contains only you just see the expansion of Lorentz series. See, in this expansion b1 z minus a, b2 z minus a the whole square, b3 z minus a. So only one term of negative powers of z minus, but the power will be 3. So power will be 3 means see pole of order m. So here it is a pole of order 3. Since the highest negative power is z minus 2 the whole to the power minus 3, therefore the point z is equal to 2 is a pole of order 3. Like this only we can manipulate pole of order 3. Suppose if it is given like this 4, pole of order 4. If it is given like this 1 divided by z minus 2, pole of order 1. Or we can call it as simple pole. Suppose if it is given power 2, double pole or pole of order 3, order 2, sorry. Okay, like this we can define. Okay, so for pole also we can different manner you can manipulate pole. An isolated singular point z is equal to a of f of z is called pole. If limit z tends to a, modulus of f of z is equal to infinity, then I can conclude that it is a pole. In other words, limit z tends to a, z minus a the whole to the power m f of z is equal to c. C should not take 0, then z is equal to a is a pole of order m. For example, f of z is equal to 1 divided by z minus 2 the whole cube. Now you can apply the limit as z tends to 2. So what happened? 2 minus 2, 1 by 0, 1 by 0 is infinity. So you can conclude that it is a pole of order 3. In other words, limit z tends to 2, z minus 2 the whole cube f of z, 1 divided by z minus 2 the whole cube, get cancelled. So what happened? The answer is 1. It is not equal to 0. See, therefore we can conclude that it is a pole of order 3. Okay, like this you can define. So last one, essential singularity. A singular point z is equal to a of a function f of z is called an essential singularity if the principal part of the Lorentz series about z is equal to a contains infinitely many terms. In other words, the Lorentz series expansion contains infinite number of negative powers of z minus a. Then I can conclude that z is equal to a is essential singularity. So this is the expansion of Lorentz series. If it is possible to expand f of z is in the form of this, then I can easily conclude the essential singularity. For example, f of z is equal to e power 1 by z. Using the series expansion, we can expand because you know that e power x is equal to 1 plus x by 1 factorial, x squared by 2 factorial, x cubed by 3 factorial, and so on. You can replace x by 1 by z. I can expand like this. In this expansion, the principal part, in this expansion, it does not contain any positive powers. It contains only infinite number of negative powers of z. 1, 2, 3, and so on up to infinity. So it will not be finite up to infinity, no? So the principal part contains infinitely many negative powers of z. Therefore, the point z is equal to 0 is an essential singularity. Is it clear? So we can prove essential singularity in different manner also by using the limit. An isolated singular point z is equal to a of f of z is called an essential singularity if it is neither removable nor pole. In other words, limit z tends to a f of z does not exist. In the first case, removable singularity, limit z tends to a f of z exists and it should be finite. If it is a polar, limit z tends to a f of z does not equal to infinity. So does not exist and it is not equal to infinity, then I can conclude that essential singularity. For example, f of z is equal to e power 1 by z. So in this, if I apply limit z tends to 0, so what happened? The function does not e power 1 by 0, e power infinity does not exist. Therefore, z is equal to 0 is an essential singularity of f of z. Like this, we can conclude. Okay, I hope that you can able to understand the idea about classification of singular points. Thank you.